So one of the nice things about the multivariate normal distribution, or the normal distribution in general, is that uncorrelated implies independence. Although we have to be a little bit careful about how we take this. So let's say if x in Rp and y in Rq are jointly multivariate normal, then x and y are independent if and only if the covariance between x and y is 0. Okay, this is a P by Q matrix. So a matrix of zeros. Or if the correlation is 0. Yeah? It's the same thing. Correlation 0 implies covariance is 0, and vice versa. So I just want you to note the word jointly here. This statement is not true without that word jointly. Okay? So for example, if x is normal, 0, 1, let's say, and z is 1 or minus 1 with probability a half, and if we let y equal to zx, then we have that y is also normal 0, 1. Now the correlation, or the covariance between x and y, is the expected value of x times y minus expected value of x times the expected value of y, which is 0. So this is just the expected value of zx squared. Well, z and x are independent, so this is the expected value of z times the expected value of x squared. Now the expected value of z is 0. This is 0. So x here is normal, y here is normal, and they are uncorrelated. But clearly x and y are not independent. Yeah, if you told me x, I would know what y was, or I'd know it's either x or minus x. Yeah, I'd know a lot about y. So x and y aren't independent here. Why isn't this result true here? Well, it's because we've not got this word jointly. Okay. X and y here are not jointly Gaussian. They're Gaussian on their own, if you like. Okay, so let's prove this. So x and y are jointly normal, multivariate normal, so we can write the vector x and vector y, if we stack them together into one long vector. So this is a multivariate normal distribution of length p plus q. Let's write down its mean vector. Well, the mean vector of x, let's say, is mu x. The mean vector of y, say, is mu y. And let's write down its covariance matrix. Now the covariance of x, let's call it sigma x. And the covariance of y, let's call it sigma y. Now we know that, let's assume x and y are uncorrelated. So that means we get zeros here and here. Okay, so we get a matrix of p by q zeros here and a matrix of q by p zeros here. Okay, so assume they are uncorrelated. Can we show they're independent? Well, the joint distribution of x and y, what we want to show this is the density of x times the density of y. That would show they're independent, right? But we can't write that straight away, so we can't assume they're independent. So but we can say that the density of x and y is the density of x times the density of y given x. Now that's always true. So x and y are independent if p of y given x is just some function of y, i.e. doesn't depend on x. So that's what we're going to try and show. We're going to think about the conditional distribution of y given x and show that it doesn't depend upon x. about that, the conditional distribution of y given x, well, that's just the distribution of x and y divided by the distribution of x. So let's write this down. We know the density of x and y. This, I'm just going to write it up to proportionality. I'm not going to bother with the bit with the determinant at the front. So this is just e to the minus a half. And if we think about expanding out the PDF with the variance matrix like this, hopefully you'll be able to see that this is going to give us an x minus a mu x transposed sigma x inverse x minus mu x minus a half times y minus mu y transposed sigma y inverse y minus mu y. Because there's no cross terms, I'm not going to get an x, y term anywhere in here. This is all divided by e to the minus a half x minus mu x transposed sigma x inverse x minus mu x. Oh, I'm running out of space here. Well, this is just proportional to, well, this is going to cancel with this. So we just get, let me squeeze it in here, x minus a half y minus mu y transposed sigma y inverse y minus mu y. Okay. So a function of y only. So this is independent of x. So we've got what we wanted. This is indeed a density only in y. So x and y must be independent. Okay, so that proves what we set out to try and prove. So that uncorrelated implies independence is just one of the reasons we like Gaussians. Another reason we like Gaussians is that they're very natural. They appear a lot of the time in statistics, primarily via the central limit theorem. So you've seen this before for univariate distributions, but there's a central limit theorem for multivariate random variables as well. So let's just say if x1, so on, are all vectors in Rp, and let's suppose they are independent, identically distributed random vectors with mean mu and variance matrix sigma, then we get that the quantity square root of n x bar minus mu, this converges asymptotically to a multivariate normal distribution with mean vector 0 and covariance matrix sigma. Okay, so this is as n tends to infinity, and this is converges in distribution. Okay, so in other words, if you add up a lot of random vectors, look at their mean vector, then asymptotically the sample mean x bar approximately has a normal distribution with mean mu and variance 1 over n sigma. Okay, so that's very similar to what you've seen for the univariate central limit theorem, but here we've got it for the for vectors. One more result we'll need that generalizes a result you've seen before is the following. Okay. So let's suppose x1 up to xn are an IID sample, independent, identically distributed sample from a normal distribution, multivariate normal distribution of length p with mean vector mu, covariance matrix sigma. Then we often use these vectors to calculate the sample mean, which I'm going to call x bar, which is 1 over n, the sum of xi, I equals 1 up to n, and the sample variance, which is the sum, well, 1 over n times the sum from I equals 1 up to n of xi minus x bar, xi minus x bar transposed, then x bar and s are independent. Okay, so you've seen this for univariate Gaussians before, that the sample mean and the sample variance are independent. We've got the same result here for multivariate quantities. So let's just sketch the proof for that. Well, first of all, if we've got these are all multivariate Gaussian, we must have then the x bar is multivariate Gaussian 2, and its sample mean will just be mu, and its sample variance will just be 1 over n sigma. That follows straight away from the proposition we proved earlier about transformations of Gaussians. Now let's let yi be xi minus x bar. This is clearly going to be multivariate Gaussian. And so what we're going to want to do is to show that the covariance between x bar and yi, we're going to want to show this is 0. Because then s is the sum from 1 up to yi transposed. So if the covariance between x bar and yi is 0, and they're jointly Gaussian, then we know they're independent. So therefore, s and x bar are going to be independent. So let's look at the covariance. Well, this is the covariance of x bar and xi minus x bar. Well, this is the covariance between x bar and xi minus the covariance between x bar and x bar. Well, let's deal with this term last here. Well, this we just said is going to be minus 1 over n sigma. So let's think about this first term. Well, this term is just going to be 1 over n, the sum between the covariance of x bar, of xj and xi. J equals 1 to n. Let's just delete this 0 a minute. Minus this. So this is going to give us 1 over n cov xi minus 1 over n sigma. That is 1 over n. Well, we know the covariance between xi and xi is just sigma minus 1 over n sigma, which is 0. Okay, so we've got x bar is normal, multivariate normal, yi is multivariate normal, the covariance is 0, so therefore x bar and yi are independent, while s is just a sum of the yi's, so therefore x bar and s are independent.